Okay, hi everyone. Very excited to be here. Thanks for having me. I'm a research scientist at Google Quantum AI, where I focus on experimental quantum error correction. So you're going to see some actual data today, and don't worry, I will go gently. And today I'm going to be discussing our recent work implementing magic state cultivation on our Willow devices. So first of all, probably don't need to review this too much with this crowd. We need non-Clifford gates for universal quantum computing. And the way that non-Clifford gates are going to be implemented, at least for our kind of near-term hardware at Google, is by using gate teleportation. So we create a high-fidelity magic state and then teleport it using C0, logical C0 here. Logical C0 here. Okay, this thing is kind of weird. To produce a T-gate, and this will enable universal quantum computing. But the challenge is that these magic states need to be very high fidelity, and such an example of a magic state here is the T-state. I'm sorry, yeah, I'm actually not very used to this. There we go, okay. The T-state here, 45 degrees rotated between two axes on the Bloch sphere. And because we don't run quantum error correction on the T-state before we consume it in the gate teleportation, it has to be natively very high fidelity. And what this means is that it sets a resource cost. So this wouldn't be a Google talk without some Gemini AI slop. Here you go. This is Gemini's attempt to depict magic state injection, which is this region over here, where you take an approach in creating a magic state that is kind of quick and dirty, where you have higher error and it costs fewer qubits and time, or less computational resources. That's apparently what it looks like. And then magic state distillation, which is where you run cross-checks on many high-ish fidelity magic states in order to produce a very high fidelity one. And we're talking like getting down to 10 to the minus 10 or so in fidelities in order to be application relevant. So this has to be, very stringent. And so before cultivation was first proposed, there was kind of this yawning chasm between the two. And what the proposal does is kind of create a bridge here where you can create higher fidelity states with not too many resources. And in doing so, you can reduce the rounds of magic state distillation that you need and maybe even eliminate it altogether depending on how our hardware progresses. We can use post-selection in cultivation. The key idea is to use post-selection to your advantage to filter the states that you want. And this is kosher because we envision a future where we have kind of a central Clifford gate processor where all the Clifford gates are running, and then we resource magic states as needed into the central POS processor from these kind of helper qubit, logical qubit patches. And so if you have sufficient qubit resources, you can use post-selection because this can be an asynchronous resource just kind of applied to the central Clifford gate processor. So each one can kind of cherry pick the state that it wants. Okay, so quickly, let's discuss what magic state cultivation is and how it works. So first, it was proposed by Craig Gidney, Noah Schutte, and Cody Jones at Google. And it starts in this small code. It's called cultivation because the idea is to start in a small code and then use that small code to check the state before then escaping into a larger code and then maybe even running a check again, depending on the noise strength, and then escaping into a larger code. And so you're kind of gradually growing the code at higher fidelity, namely cultivating it. And eventually you end up in this kind of larger code that can support the high fidelity nature of the state. And the post-selection occurs kind of in this darker blue region. You would use post-selection here on the smaller codes where it's feasible to post-select without too much of a hit and retry attempts before escaping into a larger code that can support the higher fidelity state without its idling error engulfing the state error that you just created. So what we did on our Willow processor was test kind of the initial pieces in an end-to-end program. So this includes the cultivation kind of check step here in the smaller code, and then we escaped into a larger distance 5 surface code just to show that we developed the infrastructure to do so. In practice, we'll escape to larger and larger codes as our chip sizes grow. So the physics of how it works is that magic state cultivation runs a measurement of the H operator, the Hadamard operator, whose eigenstates are magic states, and post-selects on the desired result. And the way that it runs that measurement is using phase kickback. So pretend you have a logical qubit here that might start in plus state, and you want to measure, is it really in the plus state or is it in the minus state, the eigenstate of the X operator? And you want to refine the X state. Then you can run a C0 gate here, sandwiched by 2 Hadamards using a helper qubit in order to run that measurement. So if it's in plus, this measurement will be 0. If it's in minus, this measurement will be 1. And you can post-select on that measurement result without destroying the state and refine the fidelity of your plus state. We want to do this on magic states. So we replace the C0 here with a controlled H operator right here. And in doing so, we're able to cultivate magic states. So here I'm going to be talking about magic states that are 45 degrees rotated between the Z and the X plane, and I'll get to a technical reason why later on in the talk. This is the same as the standard T state that you would expect up to just a Hadamard, which is trivial to run. So we cultivate these Z equals X states using controlled Hadamard operations. And so at the logical level, cultivating a magic state looks like you start with maybe a noisy state that you inject, and then you run this phase kickback measurement of the Hadamard operator, and you post-select on the right result. And then the state uncertainty is reduced, and the state is projected to the magic state axis. Actually, I need something to keep track of the time. Do you guys have the time? OK, thank you. OK, great. So for cultivation circuit at the physical qubit level, that's the logical qubit level, we run this in a color code at first. This is why cultivation starts in the color code, because the Hadamard operator is transversal. So that streamlines this phase kickback measurement. So at the physical qubit level, it looks like taking an ancillary helper qubit here and then doing a controlled H operator that's transversal on all the data qubits, and then decomposing that into TX T-dagger gates, because those gates are more native to our hardware. And then the challenge becomes, how do you run this controlled X operation here in a fault-tolerant way? This needs to be fault-tolerant in order to get high fidelity. So this is what the circuit looks like. We start here, where we have a density matrix rho that is an attempt at a T state, but it's not very perfect. And we then fold down our parity of the X operator across all of our data qubits in this color code, and we add these flag qubits here to make the flow with our gates work. So these are just trivially started in the plus X eigenstate, and they're included in the flow. Here we're running a T gate in order to take the X component of our qubits and transfer them into the T component in order to measure the T component. And then we run a sequence of C0 gates, which are decomposed into CZ gates using Hadamards, which kind of folds this operator. It maps this operator, the X operator of all of the qubits outlined in red here, down to a single measurement. So we map the Hadamard operator to the X measurement here. And then we reverse the process. So then we initialize in the plus state and unfold. And in doing so, because this is a time-reversed process, these measurements here on these qubits, when we add measurements here, are deterministic in the presence of no errors. So that's because we start in a deterministic state and we run this time-reversed process. They should be determined, and we use those as flag checks, and that's important for maintaining the fault tolerance of the cultivation protocol. So this is actually really a double check. The logical observable X is measured twice. You can check it by mapping these Pauli operators here. That also helps with the fault tolerance. So it's not like, we're just sensitive to the measurement error on that one qubit in the middle of the thing. We get this double check. And then, like I said, these flag checks maintain fault tolerance. So if you follow one of them here through the circuit, this orange one, let's say here, it expands out. It would catch errors. This Pauli operator would catch errors on any of these qubits outlined in orange, and then it's collapsed back to this measurement here. So it's kind of this patchwork of flags, the observable double check that maintains a fault distance of 3 in this case. And finally, I'm not showing it here, but the stabilizers are also maintained. So here we start in a color code with these 3 stabilizers for X and 3 stabilizers for Z. And if you map the Pauli operators for those, you get them back at the end. And so that means that you can concatenate cycles of quantum error correction using the super dense color code cycle in order to maintain fault tolerance as well. Can I just have a check on the time?
9:43.
Okay, great, thank you. Okay, so now how do we implement this circuit? We use transmon qubits in our architecture. And what they look like are these kind of X's here. These are capacitors. And then they're coupled to readout resonators here. We zoom in on one of them, and we see a Josephson junction, which is a nonlinear inductor that we use to make artificial atom-like behavior. Zooming in even further, here's what it looks like using an SEM. So these are tiny kind of sandwiches of silicon dioxide, which then act as nonlinear elements to create the quantum nature of our circuit. And transmon qubits are driven by flux and charge operators. They're electromagnetic circuits that are driven by magnetic and electric fields. And the way that we drive them here is with some extra lines that come into the qubit, and then we read them out through coupling to a readout resonator here. So we kind of have a chip that has a lot of these patterned on them at once. In order to couple two transmons together, we pattern them close together on the chip, and their capacitors are able to sense the electric field of each of them. And this creates a charge-charge interaction, which then we can use for a gate. In particular, we bring them to, using flux bias, to a frequency where their 1, 1, and 0, 2 levels are on resonance. So these are nonlinear inductors, so we have this nonlinear spectrum here, but we can change the flux bias to change the energy gaps in the spectrum. And if we have the 1, 1, 0, 2 transitions on resonance, where 2 is the second excited state, then we wait for a certain amount of time where the 1, 1 state goes to 0, 2, and then back to itself, picking up a geometric phase. And in doing so, we selectively get a phase on the 1, 1 state, creating a CZ gate. It all comes together by combining our chip with our control lines in a package. So here's our chip with our qubits. We have a control chip here that's printed on top. And then this is all packaged together into the fridge, which looks like this. And the fridge is held at 10 millikelvin. This is much colder than an iced coffee. And it's held together through a series of plates here of increasingly cold temperatures inside of a vacuum. And all of these cables here are for qubit control. So this is what it looks like. Yes, question?
So the packaging you showed had 2 dies. One is control and one is qubits? Or?
That's right, yeah. Mm-hmm. Uh-huh.
And then you have a flip chip on top of that, but then there's this thing to the top left.
Yeah. Sorry, which thing are you talking about?
The die to the top left.
Oh yeah, this is just kind of the package where we put it in. Yeah.
Wait, so is this like deconstructed and you play?
Yeah, yeah.
Okay.
Yeah. Okay, so now that I've explained kind of what the experimental setup looks like, let's actually show some data. So we started by just injecting a magic state, just kind of using a state injection and fault distance of 1 protocol, where we sweep the angle of the state that we want to inject, theta here, along the ZX plane, and then we perform tomography on it at the logical level by doing transversal measurements. And we see a circle, as we would expect. So here I'm plotting the components of the block sphere Z and X, and as we sweep this angle theta, we observe a circle. We can fit this circle to an ellipse in order to try to get kind of the average distance from the surface of the circle. And you can see that there's maybe a few percent or so difference. And if we post-select on all of the stabilizers, which are just given by the transverse measurements here, then we post-select with an 80% success rate, and that's constant as a function of the angle that we inject. Really what we would like to do is cultivate this. So now that we have shown that we can create an arbitrary state in the ZX plane, we want to cultivate it, namely project it to the magic axis and post-select on the correct result to improve the fidelity. So adding cultivation, what we expect to see in our simulations is something like this. This is a simulation. And you can see that as we sweep the angle theta here, no matter what angle we have, the state is projected to this magic state axis. And the reason why it's not strictly here or strictly here on the orthogonal state is because I'm simulating many shots and averaging over them. So we project the magic state axis in the simulation, and the state comes quite closer to the magic state. And now the post-selection rate depends on the angle that we injected because our cultivation step includes a detector that detects the state of interest. So we're filtering for the magic state. And this is what we saw at first. So actually, I presented this at March meeting in 2025, and we didn't understand what was happening then, but we were seeing these kind of wacky curves where, the state was kind of projected and it was beyond, the surface of the Bloch sphere. So, this obviously isn't a fidelity of over 100%. Something is going wrong in our experiment. We're seeing non-physical observables. And it took us a little bit of time, but we realized eventually that if you have coherent noise in your circuit and you run quantum error correction, then you can actually get non-physical observables, because quantum error correction in post-selection is an active process that's changing the density matrix that you characterize in the end. And so if you have coherent noise, maybe if you are running an X circuit where you measure the X stabilizers in the end, it filters for some kind of strength of the coherent noise in the Z direction. But then if you run a circuit where you measure the Z stabilizers in the end, then maybe it filters differently for this coherent noise. And this leads to two different states, actually, as a function of which tomography axis you're measuring. So you get this kind of inconsistency in logical state tomography when you use quantum error correction or post-selection. This can be shown with the detection fractions here. I don't want you to look at the details of what every single gate here is doing. The point of this slide is just to show that the sensitivity to the Z noise, which is shown in the blue here, is different for the X circuit and the Y circuit that we're running. And so this means that you have different states when you perform logical tomography. So yeah, it's different sensitivity to dephasing noise in particular. We have coherent dephasing noise in our circuits, and this comes from imperfect control as well as crosstalk and qubit frequency drift. And that leads to inconsistent states. This can also lead to different detection rates. So you detect errors at different rates depending on the axis of tomography that you are measuring. And that leads to, again, these kind of inconsistencies in post-selection and tomography. And you can simulate this using state vector simulations and adding coherent phase noise. And indeed, you see this effect happening in simulation, which kind of qualitatively matches the data. Of course, it depends on exactly the strength of the coherent noise, which isn't well characterized. But you can kind of see this effect happening in state vector simulations. If you change the coherent noise that you apply the strength slightly, it might kind of qualitatively change. But the point is that it can lead to these non-physical observables. So if you're using logical state tomography in order to characterize a state, you have to be careful if you are doing it in a fault-tolerant way where you use post-selection or quantum error correction, because you can end up maybe overestimating your fidelity this way. Okay, so we wanted to understand our data. We wanted to still use logical state tomography to check if cultivation is doing the right thing. And in order to kind of mitigate these problems, we added some echoing, which is noise decoupling, in order to echo out some of this coherent noise. And then we also worked in the XZ plane, because then we get to measure, at the tomography step, the stabilizers, the tomography measurements match the stabilizers of the code, which kind of makes the sensitivity to these noise sources more symmetric. So yeah, so now we're in the XZ plane, and you can see that there's roughly the same amount of blue. This isn't 100% mitigation, but it helps. And then we add echoing, where we add a whole bunch of pi pulses into our circuit that are halfway between pairs of Hadamards on our qubits. And in doing so, if there's a coherent phase noise, it's kind of echoed out, at least in this pair. Of course, we're running non-Clifford circuits here, so we need to propagate the Pauli frame changes to just before each non-Clifford layer and invert it for consistency. And we do that. Okay, so here's what we started with. This is all simulations, just to check that what we're doing is kind of making sense. We started in the XY plane with no echo, and we see something like this. Going into the XZ plane, things start to look more symmetric, as you'd expect. And then echoing, things start to collapse down to the magic state axis. But note that we can still see non-physical observables, and this is because our echoing is imperfect. Our circuits aren't exactly time symmetric, so you can't perfectly echo out all of the noise. They don't have the symmetries that you would need to do so. So that means that we can't use logical state tomography to characterize our state fidelity rigorously, and I'll touch on what we use instead in a second. Nevertheless, we ran the experiment with these mitigations, and this is what we saw. So the red curve here is just state injection. Our simulation is gray, I already showed you that, and then cultivation is now the blue data. And you can see here that it approaches the T state more closely. Again, we're not using this in order to quote a state fidelity because we haven't characterized our coherent phase noise carefully. But you can see at least that it's moving closer, and it bypasses in particular this line, which represents just state injection. Here I'm simulating depolarizing noise with a noise strength of 3 times 10 to the minus 3, which matches our hardware. The post-selection rates here match. And this is actually how we tune our P. We tune our P in simulation to match the post-selection rates, and then just see what kind of state behavior we end up with, to not cherry pick that. And indeed, the post-selection rate is maximized when we inject the T state, as you'd expect. This is the state that cultivation is filtering for. And it's minimized at the orthogonal state at the angle 5 pi over 4, again, as you would expect. And so, okay, now for application relevance. This is the kind of circuit where you would be running state injection and then cultivation, and then filtering at the cultivation step, but only running cultivation once at distance 3. In this case, we get about 50% acceptance rates for quantum algorithms. Okay, so now we want to quantify our T-state fidelity. How well are we doing? How far do we have to go in order to get application relevance? And that's what I'll discuss here. So in order to do that, as I've harped on, we do not use logical state tomography, but instead we actually use cultivation as a metrology tool in order to measure the T-state fidelity. And it goes like this. We start with a prepared cultivated T-state, just what I showed you just now. And then we run cultivation more times in order to measure it along the T-state axis, because it's this measurement that we need in order to measure the state fidelity. You prepare a state, you want to measure it along its axis in order to get the overlap with that axis, and then that gives you the state fidelity. And here we have 2 rounds of cultivation to maintain the fault tolerance. It turns out that if you just run cultivation once to do that measurement, you need to check that measurement that you just did along the magic state axis, and so you run cultivation again. And these QEC cycles also help to maintain fault tolerance. So this whole circuit has a fault distance of 3, as the cultivated T state should. All right, so this enables an upper bound of the state infidelity in a single self-consistent measurement, because we're just measuring directly the component that we want to check. And I say upper bound because the measurement apparatus, this kickback tomography apparatus here, will also natively have some error. And it also mitigates projection noise. So this was actually crucial to get our fidelity estimates in practice. If we just stuck with logical state tomography, we'd need to average down the binomial distribution in order to resolve our, our high fidelity states. And if you have an error of, say, 10 to the minus 4, that means you would need roughly 10 to the 8 shots in order to average down the noise. But here, because we're measuring directly along the axis of interest, the binomial variance is narrowed, and we're able to resolve our T state with roughly 1 over epsilon shots instead of 1 over epsilon squared. And this kind of actually enables our fidelity estimates in practice. Okay, so but first, before measuring a cultivated T state, we check it on just a state that's injected. And the point of this is to just kind of see, is the kickback tomography measurement apparatus working as we'd expect? So we start with an arbitrary angle theta that we inject. We run some QEC cycles, and then we run this kickback tomography measurement. And here I'm plotting this on a linear scale just because we should see a sine wave, and we do here in the data. And this is because we're just projecting the state to the T-state axis and then measuring the overlap. So you get this kind of sine wave of projection. The data retainment rate here is 20%. For all the data I'll show for kickback tomography, we are post-selecting on all of the detectors in the circuit. So this includes the kickback tomography detectors because we need this to be, as high fidelity as possible. Okay, plotting this on a log scale, we're able to resolve that an injected T state has a state error of roughly 4e minus 3. And this makes sense because the circuit has a fault distance of 1, and this is on the order of our gate error, our single qubit gate error. Our physical qubit gate error. Another check for kickback tomography is that we simulate the whole circuit and then sweep the noise strength in our simulation to check the scaling. And you see here the simulation results shown in blue, and then I just fit to a cubed polynomial in order to show that indeed the scaling of the logical error that we observe here is p cubed. These error bars are 1 standard deviation. So with this we were kind of comfortable showing that kickback tomography behaves as we would expect on a kind of simpler state, and it scales as we expect, so then we applied it to a cultivated T state. And this is what we saw. At the T state here where we are injecting pi over 4, we get about a factor of 40 improvement when we add cultivation. So this kind of also shows our below threshold nature of our quantum error correction, in that adding quantum error correction, gadgets actually improves things. We're using post-selection to our advantage here as well. And in particular, we get state errors of roughly 10 to the minus 4. This is a bound, remember, because we're using kickback tomography to measure it. And the data retainment rate is again maximized as you would expect at the T state and minimized at the orthogonal state. So things kind of make sense. After post-selecting for all the detectors in kickback tomography, we get a post-selection rate of about 8%. This matches our simulations. If we just take a very simple depolarizing noise model and we simulate this circuit, we get this agreement. Again, I've tuned this P to match the post-selection rate and then just see what state fidelities come out and they match. So it's kind of nice to show that things are making sense. And then I wanted to point out that actually these QEC rounds are really important for maintaining the performance of the state. So if we actually take these away, we actually remove the fault-tolerant kind of code that we use in order to maintain the state fidelity. So let's see what happens, if we take away these QEC cycles. What we're doing is removing the stabilizer measurements. And so we prepare stabilizers in this circuit in the injection part here, but they're never measured because cultivation doesn't measure the stabilizers, remember, it just maintains them. So the stabilizers remain open through all these cultivation rounds, and then they're just measured at the end. And this has a fault distance of 1. So yeah, so they remain open. And this is what we see. This is this dark blue curve here. It actually is a factor of 100 worse. So the underlying structure of the color code here, which we use to measure the stabilizers, is crucial here for maintaining the state performance. And this is, again, a sign of the below threshold nature of our QEC. I also wanted to point out that, in principle, you don't need every QEC cycle in order to maintain the fault distance of 3. You can get rid of these two, and then keeping these 2 QEC cycles allows you to kind of catch all of the distance 2 and distance 1 error mechanisms that could appear in the circuit, and you maintain a fault distance of 3. So the stabilizers remain open here for longer, but they are measured in the circuit. So the longest the stabilizers remain open are through these 2 rounds of cultivation. And in this case, the state fidelity is 50% worse than if we keep the QEC cycles, but it's only 50% because, again, the circuit has a fault distance of 3. And the post-selection rate is higher because there are fewer detectors. And the kind of, so here I'm showing the data here. The purple is this case without these 2 QEC cycles, and the cyan is what I showed before of our usual circuit. And it kind of matches simulation. We see this gap in simulation as well using the same noise model, the same simple noise model. And we attribute this difference to the fact that these detection regions here are open. So we prepare the stabilizers. They're measured here, but then they remain open through many, many gate layers here, roughly, how many is it, like close to 30, and a bunch of measure and resets. And so they're just accumulating errors, and the detection fractions are larger, and the decoding is harder. And so we see slightly worse performance, even though the fault distance is the same. This whole circuit was calibrated. All the circuits actually in the paper are calibrated through reinforcement learning. So here, I mentioned that we have a whole bunch of transmons on a chip, and they're controlled with electromagnetic fields, and the gates are done with flux bias pulses, and so there's a lot of free parameters in how we control our circuit and how we read it out. And maybe someone could say something, or, okay, it's gone, okay. So we calibrate our parameters using reinforcement learning, where there are multiple reinforcement agents that minimize the detection fractions in the QEC circuit. So this is kind of what we call in-context calibration, where the control parameters are optimized in the circuit that we're running. And this actually made a huge difference in that the detection fractions, our rate of detecting errors, was reduced by 30% with reinforcement learning. And the performance in this state was drastically improved. This is an A/B test where I ran a comparison with and without RL control at the same time. And you can see here that there's close to like a factor of 5 difference in state performance and close to an order of magnitude in how often we declare success in our detectors. Okay, so everything that I just showed is in a color code so far, a distance 3 color code. But our quantum computer works in a surface code. And the reason is that is several reasons. One is the surface code is matchable, so the decoding step is easier. And the threshold is slightly higher. And then there are well-studied qubit dropout schemes. Sometimes our qubits break and we need to remove them from the circuit, and there are schemes that you can kind of get around this in a surface code, but it's still a work in progress in the color code. So we want to transfer our state to the surface code, excuse me. And the way that we do that is we start with our state injection and our cultivation, and then we run some extra QEC rounds kind of in something called a grafted code, which is compatible with a surface code here. And it starts with an extension cycle where we initialize a whole bunch of qubits in the Z basis in this top triangle here, and the X basis in this bottom triangle here. Think of kind of like your state injection protocols, how they work, where we're injecting now a cultivated T state. And in doing so, in preparing the Z stabilizers up here and the X stabilizers down here, we're preparing as many stabilizers as possible. So for example, in this square here, the Z stabilizer is determined because we initialize in the Z basis for all 4 qubits, and so we can use that even in the first round in order to detect errors. And then we run a grafted code, which is kind of similar to a surface code in this region and similar to a color code in this region, and it maintains the fault distance I'm sorry, if you run the grafted code by itself, it's a fault distance of 5 actually, because our code here is a distance of 5. But ultimately the whole circuit is a fault distance of 3 because we start in a distance 3 code. So the point is that we can kind of transfer a higher fidelity state that's too high fidelity for its distance 3 code into a larger code that has a fault distance of 5. And here's what the data looks like. Again, we start with a simple injected state. And those are the red points here. And they kind of match simulation, which is shown in the gray points here. And this is sweeping the angle theta that we inject. And we maintain about 50% of the data. Here I'm post-selecting only on the stabilizers, only on the detectors that are in this initial step in the distance 3 code. As you start grafting to higher codes, it becomes impractical to post-select just because you would always detect an error because the code is larger. So here the data is decoded using Tesseract for the remaining data sets that are filtered after post-selection at the distance 3 for the distance 5 circuits. So these simulations were done using a package called QEvol. It's worth pointing it out in particular because this is a state vector simulation across 54 qubits. And the way it works is just kind of using a linear combination of Pauli circuits and creating linear combinations when you need to, when a non-Clifford gate arises, and then adding depolarizing noise on top of all of that. And those were, this package was developed by my colleagues, Leonid, Ming, and Devere here. So okay, so what happens if we cultivate a T state now and then graft it into a surface code? We see something that looks like the following, where here I've shown in the light cyan just cultivating and then grafting and running 2 cycles in the grafted code. The dark cyan is 3 cycles in the grafted code. And again, state injection here is shown in red. And you can see that the state is kind of squished closer to the T-state axis. It doesn't go past the origin, which is an effect that we see in simulation. And this just has to do with what chains of errors can get through in the particular circuit that we have. Because think about injecting, exactly the wrong state. This will always light up a detector, and so the detectors become saturated, and you have like a very high rate of certain error chains that can get through. So, okay, so if we focus closer to the T state here, you can see that now none of the cultivated T states extend past the red data, past the injection data. And this is expected. This is because now our state fidelity is limited by the distance 5 idling rate in the grafted code. So the grafted code just isn't large enough to support the high fidelity of our cultivated T state. And this is what we expected. Of course, we'll be grafting to higher states as our chips grow, but for now, this is what we have. And then we can run a memory experiment, actually, where we inject a T state, cultivate it, graft it, and then remain in the grafted code for n rounds. And we can fit to an exponential, and we see a logical error rate of 5% actually here for our distance 5 code. I'll discuss that more in some detail in a second. And again, our post-selection rate is sinusoidal, as you would expect when maximized when we inject the T state. This actually does not match simulations very well for the noise model that we injected. And the reason is because of population leakage outside of the computational subspace, which is not included in simulations at this stage. So if we don't include leakage and we include a depolarizing noise model, we should have a much better logical error rate. And the state should be kind of closer to the axis here of the magic state. The way that we know that population leakage is a problem is by looking at the detection fractions and how they change over time. Here I'm plotting in the grafted code, running for 9 rounds in the grafted code, what the detection fractions look like. And you can see here there are all these there are some smaller detectors here. These are starting in the distance 3 color code. These large detectors here, this is the cultivation detector. So this is the one that's checking the magic state in the distance 3 color code. And then all of these detectors here are the memory experiment in the grafted code. And you can see in experiment that they shift up slowly over time. This is a sign of some kind of correlated error. Population leakage is a correlated error in time because the excited state population is long-lived. And this effect does not show up in simulation where we only include depolarizing noise. Another way, yeah.
I just ask, on that previous graph, what's the sawtooth detector? There's one of them seems to be like a sawtooth wave. It's going up and down, up and down.
Oh, yeah, this is SPAM. This is state preparation. So this is because our measurement of the one state is different. Okay, so, right, so, okay, yes, another way we can tell that there's population leakage is by looking at the correlations between the detectors. So here in the experimental data, what I'm plotting here is one detection rate on one axis and another detection rate on the other axis, and we're plotting the covariance matrix between the detectors. And what you see are these kind of like red splotches here. And that's because these detectors are time correlated. So if you were to zoom in, there's too much data to show here, but if you were to zoom in on one of these boxes in the covariance matrix, there are a whole bunch of pixels, and those pixels are the time axis. So whenever you see a big red splotch here, what you're seeing is correlations in time. So we look at this and we say, oh, okay, there's probably some population leakage, and this, again, doesn't show up in simulation. So in the future, we're going to debug this leakage. There are some circuit optimizations that we can run in order to mitigate it probably almost entirely, and we're not too worried about this, but we kind of understand our data, and we understand that we're able to graft a t-state into a color code, surface code. All right, so in summary, I discussed cultivation. It's a check of the logical observable. It's a measurement of the H operator. It includes post-selection to increase the fidelity of the state. And we developed these modular tools in order to run pieces of cultivation circuits in QEC and combine them in different ways in order to show what cultivation is doing in logical tomography, and then quantifying it in kickback tomography, and then grafting to a surface code. This was enabled by the reinforcement learning calibration and simulation, state vector simulations developed by my colleagues. And we used cultivation as a metrological tool in order to measure the state fidelity in a single self-consistent circuit. We see an improvement when we do so by a factor of 40 and 10 to the minus 4 state errors. And finally, we were able to transfer into a grafted code for compatibility with our surface code quantum processors. In the future, there's a lot of opportunity for improving the performance even further. So one thing we can do is study exactly what RL was doing. We just kind of gave it the circuit, and it's a little bit of a black box right now, but we can understand in more detail why it improved things so much, and then use that to refine our calibration protocol. Also run some sensitivity analyses to different noise sources and further circuit optimizations resulting from those, and optimize the parameters for tesseract for grafting. And as I mentioned, reduce the population leakage that we see in grafting using some leakage removal gadgets and circuit optimization. And in the future, there's a final step in the original cultivation protocol that I didn't discuss yet, which is transferring into a matchable code. So far we've only shown a grafted code, which is not matchable and decoded with tesseract. We need to stay in that grafted code for roughly d rounds of the final distance of the code that you're in. But ultimately, we want to switch to a matchable code, and that's done with a slightly different circuit. It's discussed in the cultivation theory proposal. We need to do that step as well at some point. And grafting into larger codes to support the high fidelity nature of the T-states. Eventually run a real-time T-gate, of course. And also I just want to point out that kind of looking towards the future, the cultivation circuit is a fault distance of 3. So if you took the noise strength that we see in our processors now, and you run a simulation and you see the 10 to the minus 4 state errors that we see in experiment, and then you have it, you get close to 10 to the minus 5 state errors. And for chemistry, maybe we only need something like 10 to the minus 6 state errors. So we're actually surprisingly kind of approaching this regime, even with just a factor of 2 noise processor improvement. So cultivation is really a powerful tool here to approach specific application relevant T states in maybe the not too distant future. We're hiring, so if you are a student and you're interested, we're hiring postdocs and faculty, anyone who's interested. Go to this website and come talk to me if you would like, and you can see my email here. We're looking for people across the gamut, experimentalists and engineers, but for you guys, also some theory folks for algorithms as well as error correction. And this was really, a team effort with my colleagues. Craig was my mentor throughout this project, and I just learned so much from him. He's an excellent mentor and very kind. And then my QEC sub-team here, Alex and Gabrielle and others, they were really able to help with the calibration of the processor and kind of act as a sounding board in the process, and I couldn't have done this project without them. My manager, Kevin Satzinger, oversaw the research and directed it and kind of decided to do this project in the first place. So it's thanks to him that we had this opportunity. And of course, Google Quantum AI for the world-class Willow processor that enabled this work. I'll take questions.
Yeah, thanks for the great talk. I think some hand here was first. Anthony? Yeah.
Sure. Thanks, Emma, for a great talk, and congratulations on the great result.
Thank you.
I'm curious about if there was an agreement between what you saw experimentally and with the full state vector simulations and with Craig's original simulations when he S state instead of the T state.
Yeah, that's right. Yeah, so he simulated 10 to the minus 3 depolarizing noise. And if you scale our simulations by this factor that you need with the fault distance of 3, the difference was 2.3 cubed, you get exactly Craig's result.
Yeah, right. So you can inject the S state, because he said we made a bunch of assumptions saying if we inject an S state.
Oh, I see. No, we didn't inject an S state. That's for the T state that he simulated. Because he did simulate, I was just comparing the ungrown T state that he simulated. He simulated T states at circuits with a distance of 3, and that's what matches. We didn't cultivate S states here. It would be an interesting thing to check, because as you point out, there was a factor of 2 difference in the cultivated S state versus a cultivated T state. And we think, talking to Craig, we think it's maybe because the stabilizer, this is just kind of a hypothesis we haven't tested yet, but we think it could be the fact that the stabilizers are actually in superposition during cultivation, because the T states, the T gates that we run, put the stabilizers into a position of moved around and not moved around, which might change the sensitivity to errors, but maintain the same fault distance. So that would be an interesting thing to check.
Thank you.
Yeah, thanks for the question. It's a good one.
I'm curious about why, because I think it's not lost on me that you've done all this work for a platform that has native arbitrary Z and X rotations, for a transmon. And so I'm curious about why you've gone down the kind of magic state cultivation route to give you the kind of non-Cliffordness that you need with universal gate set. Did you take that somewhere?
Yeah, that's an excellent question. So you're right that we have arbitrary native Z and X rotations. The calibration is challenging, but they exist. And those are at the physical qubit level. Everything that we're doing here is at the logical qubit level, where we're encoding into a color code or a surface code. And in doing so, the logical operator is spread across many of those physical qubits. So in order to run an arbitrary logical rotation, we would have to run an arbitrary XXX operation. And that's much harder to do. A 3-body, arbitrary X rotation is much more challenging. You'd have to go through sorry, what?
The overhead is worth it in this case, instead of doing these kind of simultaneous single qubit rotations.
Oh, it's not a simultaneous single qubit rotation. It would be a joint 3-body rotation. And those are hard to engineer. I mean, you would have to, we've thought about it a little bit actually. You would have to kind of move the couplers and engineer this kind of interaction across a whole bunch of measure qubits and couplers to get to the 3 data qubits. So if you wanted to do an arbitrary XXX 3-body interaction across 3 data qubits, you'd have to go through, I think it's 4 couplers and 2 measure qubits. And then they'd have to be brought all on resonance together, and you would have to couple through to a common mode between all of them, and the fidelity would probably be terrible. Oh, yeah, thanks. Yeah, thank you for the question. This had us puzzled for a while, so I appreciate it. Okay, maybe this is the best way. Yeah, so when we are running logical state tomography, we run our circuit twice. Once where we measure the X stabilizers at the end, and once in this case where we measure the Y stabilizers at the end. This is the case where we're preparing a T state in the equator of the Bloch sphere. And so when we do so, we have different detection regions throughout the circuit. So here what I'm showing is the detection regions, the sensitivity to different types of noise throughout the circuit. If you were to zoom in on these plots, you would see a whole bunch of gates. And each box here is like a tick, a clock tick. So there's a different gate at each clock tick here, and the detection regions change accordingly. What a red detection region here means, let's say, for example, here, means that if there is a Z error on this qubit, then the X stabilizer would pick it up if there's a Z error at that time on that qubit. And so you can kind of glance at these colors and use it as a way to understand what is the sensitivity of my detector to different noise sources. And now, if we do the same with the Y circuit, you can see that the sensitivity is different because the colors are different, the detection regions are different. And ultimately, that comes out of the fact that we're measuring different stabilizers at the end. And those stabilizers need to be determined, which propagates the difference in the detection regions backwards through the circuit. So now if you think about, okay, let's say I have correlated coherent noise. Then maybe, as that noise is traversing through the circuit, these detectors pick it up more often than these detectors. And then we're post-selecting on the detectors. So we're filtering we're filtering the noise differently for the two different states. And so now if we filter coherent noise differently for the two different states, we can actually end up with different logical states at the end. Because coherent noise can cause these coherent rotations of the logical qubit. And if it's filtered differently, maybe you actually have different logical states at the very end. And then those different logical states lead to non-physical norms.
And here you're just doing so you're doing tomography in the XY plane here,
Mm-hmm.
and then you get two different states at the end.
Yeah, so the sensitivity, so these detection regions have different sensitivity to noise sources. But then we switch to the ZX plane to try to make it more symmetric. It's not perfect because it's not like the detection regions match exactly. Then we'd have to run the exact same circuits and we wouldn't be able to measure two different axes. But it's a bit better and we see the impact of that in simulation.
Thanks. I had a follow-up question. How susceptible are your post-selection during the cultivation steps to readout error?
We didn't do a sensitivity analysis. That's one of the things we want to do in the future, is understanding what these error sources are like, how they fit into the error budget of the T state. And we could do that through simulations. The whole circuit has a fault distance of 3. So that means that if you do have a readout or a reset error, you would need at least 2 other simultaneous errors in order to cause a logical error. But I don't have a sensitivity analysis for you at this stage.
But
Yeah.
you feel that these non-physical logical observables that you
Oh,
readout errors and tomography?
no, it's not. We ran a whole bunch of experiments actually to check that. So if you change the state that you're doing tomography on, so that you have different states that you read out in the end, you still see the same effect. We even did things like invert the qubits at the very end before the measurement and then check to see if we still see this effect, and we do, yeah.
I'm curious about your decoder optimization. Like you said, you think you could optimize test-right to even get better results. But I guess you could also argue that there's lots of development of neural network decoders with Google, and I'm
Totally.
wondering if you tried this or.
No, we do want to try it, yeah. We haven't tried it. That's a very interesting direction that we're also thinking about, yeah. Yeah, there could be some, there could be some immediate improvements from that. One thing that would be very interesting is, our data contains population leakage, as I showed. So maybe the neural network decoder can actually pick that up.
Actually, a question related to that, so I'm using my privileges. So, was the decoding done offline, and
Yes.
Presumably you need some like high throughput decoder when you're doing this in practice. Is that true? Or?
Yeah, so that's an additional, enormous challenge that we'll have to overcome.
Right.
We demonstrated in late 2024 in our below threshold QEC result that we are able to decode online for a surface code memory experiment. As our decoders change, we're going to have to, identify decoders where they work online, particularly in the grafted code, and that's going to be a challenge moving forward. Online, it's not a black or white thing. It's like how much delay are we willing to tolerate? And that'll depend on how many qubit resources we have, how many magic state factories we have, how long we're willing to wait, things like this.
The grafting step, is that the most challenging decoding step, or the step for decoding?
Yeah, because in the color code, we post-select on everything, which I think we'll do in practice as well. So there is no decoding in the color code. It's all grafting and then switching to a matchable code, so yes.
Thanks for a great talk. I have a question about the kickback tomography.
Oh, yeah.
So there, the idea is that you are using sort of the magic state preparation circuit as part of the measurement.
Yeah.
And so just playing devil's advocate, I mean, that type of tomography scheme is susceptible to a systematic error in that.
Exactly. Yes, I agree. That's why we ran logical tomography as well, to check that cultivation is behaving the way that we expect, and why we went through all of that effort to make sure that we were able to understand the data even in the presence of coherent noise, and that it kind of matches simulations. So from the logical tomography, we were kind of confident that, okay, at least the action that cultivation does on the logical block sphere kind of roughly makes sense. Yeah. But we racked our minds trying to think of what systematic error could cause something that could lead us astray, and we couldn't come up with anything. If you think about, okay, one that we thought about was, all right, maybe during cultivation here, there's a layer of physical qubit T gates at the beginning and at the very end during the cultivation step, because we do T gates on all the data qubits, we fold down the X component of the logical observable, we expand it back out, we do a T dagger gate. What if those T gates are all overshooting or undershooting slightly? That would actually be physical qubit gate errors, which would then be picked up by the stabilizers. So it's another way of thinking about why the underlying color code and the quantum error correction associated with it is very important, because if you were to systematically overshoot or undershoot single qubit gate errors, they should be picked up at least to first order by these QEC cycles. The fault distance of 3 helps with that.
You mentioned you noticed some signature of leakage errors. And I think in another Google paper you had some leakage reduction process.
Absolutely, yeah.
Did you use that, or is it compatible with this?
We didn't use it in this data, and that's just because of, but you're right, and I mean, I mentioned in the Outlook that we can run some circuit improvements and include these kind of leakage removal modules. That's one of the improvements that we want to do. I kind of glossed over it, but this extend cycle actually has a different set of reset and measure qubits than the grafted code cycle. And the reason why we did that is because we had this geometry of the color code to start that we did all of our cultivation measurements in. And then we used the design of the grafted code stabilizers here on the edges there actually aren't that many choices for how to design the circuit and the gate. It's quite challenging in order to maintain the fault distance of 5. So I took the stabilizers here from Craig's paper, from the circuit, the crumble circuit in the grafted code. And that was only compatible with a different geometry of the color code. So here you can see here, it's kind of swept under the rug, but you can see these black arrows right here. These are extra swaps that we're adding. And the reason is that we don't have the connectivity on our chip to actually couple the data qubits in the geometry of the standard hex lattice. And so we add some swap gates between these pairs of qubits in order to match our chip layout to the geometry of the color code. But there are multiple choices of which swaps you can do. Like in this region, if you look at this region of the color code, it's these 3 pairs of qubits that are swapped now in those instead of those 2. And that means that we actually have a different geometry of the color code. We switched to a different geometry of the color code in the grafted step compared to this initial step. And that meant that we have a different entire set of measure and data qubits, the lattice parity kind of swaps between these 2 steps, and we think that this is contributing to leakage. But the fact that that swaps means that we weren't able to add DQLR, this data qubit leakage removal. We should be able to re-optimize the cultivation circuit in order to account for this and then add DQLR in the future. We haven't done it yet.
Just wanted to ask again about the sort of non-physical states.
Yeah.
So there's this well-known effect in physical tomography that the further you are away from the measurement axis, the more likely most estimates of the state go outside the Bloch sphere.
Yeah.
When you do logical tomography, have you ever seen, if you do it aligned with the measurement axis to compare a state aligned with the measurement axis through rounds of error correction, do you ever see, in that case, the state going outside the Bloch sphere?
Yeah, so what you mentioned is an effect of the binomial distribution, right? Where you have some statistical error and the variance of the binomial distribution increases as you go off the axis of measurement. In those simulations, we ran a ton of shots to try to average this down and see if we still see the non-physical nature, and then compared to the distance from the origin, it's way more than described by the binomial distribution. So this is not a statistical effect. Even if you ran infinite shots, you would still see this non-physical nature, meaning that if you ran tomography on if we prepared an X state and then ran tomography in the XY plane, we could still, in principle, see these non-physical norms because the slight sensitivity differences to noise sources. If the state was slightly off axis from X or Z.
But does it disappear when you go on axis with the measurement?
If we go on axis and just perform that single measurement, then no, that would be physical because that would just be a mean given by the binomial distribution, which is always less than 1. And that's kind of the spirit of the kickback tomography.